Welcome back to the smartest year ever, our quest to become the world's greatest conversationalist. My name is Gordy, and I was just wondering, what is the deal with the speed of light? How did they first measure it? How do you measure something that fast? And why is it always the same? Before we get into it, like and subscribe right now if you haven't, so you can keep up every single day. I do this every single day, and I'd like to see you tomorrow as well. The femtophotography post on May 3rd, the MIT lab's ability to photograph light moving, got me really going down this proverbial wormhole, so let's get right into it. All right, you're driving 60 miles per hour, and you flip on your headlights, so now that light is moving 60 plus 186,000 miles per second, right? Wrong. No matter how fast you're going, the light from your car still moves away from you at the same speed, always. So how is that possible? Well, for centuries, people thought light traveled instantaneously. Even Galileo tried to measure the speed of light using lanterns on a hilltop. But the timing was just way too fast for you to, see the lantern? And I remember being 6 years old and learning about the concept of speed of light, knowing that basically all I knew was it's the fastest thing possible. I remember asking my dad turn on and turn off the living room lamp and seeing how far I could sprint across the room while the light flipped on and off. And I don't know, we basically got as far as Galileo. The first real breakthrough came in 1676 when Danish astronomer Ole Rømer noticed something weird while observing Jupiter's moon Io. Io is the super volcanic one, tidal heating, if you remember from astronomy courses. Its eclipses happened later when Earth was moving in an orbit away from Jupiter and earlier when Earth was moving towards it. So the only thing that explained that delay was that light must take some time to travel. Rømer estimated it took light about 22 minutes to cross the diameter of Earth's orbit, and he was off on the number, and we know modern it's more like 16 and a half, let's say now, but he wasn't off on the idea being that light actually has speed. All right, fast forward then, or time travel I guess, to 1849, and French physicist Hippolyte Fizeau, Hippolyte spelled like hippo-light, cool name, maybe the smartest year ever, coolest name of the month, we'll see. But Hippolyte Fizeau, he figured out how to measure the speed of light right here on Earth. And he did this by he shined a light through a rotating toothed wheel toward a mirror that was 8 kilometers, basically 5 miles away. And by speeding up this rotating wheel until the returning beam got blocked by the next tooth of the wheel, he could clock the round trip time that it took light to travel. And as a result, about 313,000 kilometers per second. That number got refined by Albert A. Michelson, born in 1852, who used rotating mirrors and longer distances to get even closer to the correct value. Today, we know the speed of light in a vacuum is 299,792,458 meters per second, or 3 times 10 to the 8th meters per second, if you want to go scientific notation and make it a little simpler. And if you're like me, so you're saying, all right, if the speed of light, c, is constant, then why would it matter if it's measured in a vacuum? So that was my question. All right, you say the speed of light in a vacuum, but you say it's constant. How does that work? Well, because that constant, c, as I said, only applies in empty space. And in air, water, or glass, light still moves at c between atoms, but it gets absorbed and re-emitted along the way, which slows its net progress. The medium doesn't change the straight line distance, but it adds interruptions, so the effective travel time increases, making the average speed appear slower in something like water. So yeah, light follows the same rules, but only in a vacuum does it really hit its full stride. So then you might think, hey, all right, if speed is just distance divided by time, and time is relative, then how is the speed of light not relative to? And this is exactly what Albert Einstein tackled in 1905 with his theory of special relativity. He proposed that light's speed is constant no matter who's measuring it or how fast they're moving. It's not that light doesn't follow the rules, it's that light sets the rules. To make that constant speed possible, time and space themselves actually stretch or shrink. That's pretty mind-blowing. We're getting into some real theoretical, wild, what are the rules? Are there rules? What can we know is true? So if you are moving close to light speed, close to the speed of light, time is actually slowing down for you, and lengths contract. That's so science fiction-y, but it's been confirmed in labs, particle accelerators, even GPS satellites, which have to account for time moving slightly differently in order to avoid drift. So it's real. That's wild. Another question you may be asking, or what I was asking, was why is light the fastest thing in the universe? Like, why did light get this amazing title? Why is light the common denominator of the most crazy, like fast, that's the ultimate thing in the universe? Why can't anything outrun light? Like, why is light the ultimate constant of the universe? Well, it's not just fast, it's the universal speed limit. Any particle with mass requires more and more energy to go faster. At light speed, it would require infinite energy. And photons, the particles that make up light, have zero rest mass, which is they have zero mass at rest. So they always travel at this maximum speed. So it's not just light that's special. It's that massless particles have no choice but to travel at the universal speed limit. Light just happens to be the most familiar example. C isn't necessarily just the speed of light, it's the speed of causality. The fastest anything can go in the universe, the universal speed limit. It's like the rule maker. It is the one rule that it's like, all right, this is the rule, boom, here's the universe. So the speed of light isn't just a big number, it's the hinge point of causality, physics, and how we understand time itself. It's pretty mind-blowing. But so there you have it. From a moon of Jupiter to the edges of space-time, the speed of light isn't just how fast light moves, it's the one thing in the universe that never changes, no matter how much everything else does. And big caveat, this is beyond my college physics understanding. We operate in more of a familiar frame of reference in college physics. You know, this frame of reference is more familiar to us. So I really welcome any input of any like theoretical physicist or any physicist or anyone who studied this and read about this that can elaborate or refine on anything I said. I really appreciate it. You know, it's a very, very heady topic. And I would be lying if I said I fully understand or grasp all the implications of it. So I still really struggle with the concept of space-time a little bit. So I totally welcome anyone who wants to shed a little bit of light, so to speak, on this topic. Because I know I'm going to get actually'd like a ton for this one, and I am all for it. Please, actually me, because teach me something. I majored in English and the medical sciences. You know, I know biology, I know the physics, I know biochem, orgo, stuff like that. But I got the foundations for many disciplines, but admittedly, I do lack depth on this topic, and it probably deserves a lot more depth. In the meantime, also go check out my femto photography episode from May 3rd, and also check out the short version of this one on YouTube Shorts, TikTok, Instagram. And thanks to all my sources, which can be found in the YouTube description. Leaned heavily on my sources because this is I would say this one took the longest for me to write and conceptualize because there are so many questions I had, and it took me a really long time to actually understand it and like break some of the rules that I thought existed in my head to encompass a different frame of reference, like on a universal scale or not on Earth and things we can observe. But anyway, please leave a comment, follow, rate, like, subscribe, share with someone who likes this sort of thing. That would be really appreciated. At Smartest Year Ever on YouTube, Spotify, Apple Podcasts for the full-length episodes. At Smartest Year Ever on TikTok, Instagram, YouTube Shorts for your daily clips. In the meantime, stay curious and stay clever on our quest to become the world's greatest conversationalist. I will see you tomorrow in the smartest year ever.